In this video, we're going to introduce the concept of gases and cover a lot of familiar information regarding gas laws, the ideal gas law, and partial pressures. So there's a lot of information to cover in this video, and you can notice right away at the top in the right corner, there is a lot of vocabulary terms. There are a lot of vocabulary terms that you need to add to your Quizlet or cram.com accounts. Pressure, the P and T relationship, this stands for pressure and temperature relationship, volume and temperature, pressure and volume, what is an ideal gas, what is STP, what is partial pressure, and what is a mole fraction. So we'll cover those over the course of the video. First thing, gases. Okay, we know that gases are all around us, and even though we can't see them necessarily with the naked eye, their atoms are there, and we can measure their behavior. So for example, if we zoomed in on this balloon here, and we zoomed in, let's just say on this little part of it where there's some molecules inside, we would see gas molecules floating around. And we can just pretend that these blue ones, let's just make it up, are helium, and these red ones are just oxygen, for example. We know gases are moving, the molecules of a gas are moving in a very specific way. Okay? And the theory that describes their movement is called kinetic molecular theory. And kinetic molecular theory tells us a few things about gases. Number one, okay, the molecules themselves have no volume. So this molecule right here, this blue dot, technically it takes up some space, as we can see. But what we're going to assume is the volume, the amount of space it takes up, is so small compared to the whole space that it essentially has no volume. So molecules have no volume. Okay? They also move randomly. Molecules have random motion, they move fast, and they collide with each other. So if we were to represent the motion of these molecules, maybe this oxygen molecule goes going boom, it's traveling in a straight line until it hits either the wall of the container and bounces off, or if it hits another molecule and bounces off. And we know that all these molecules, boom, are flying through at incredibly fast speeds, bouncing off each other. And as a result, we can measure a lot of quantities about these gases and predict behavior about them. So the first thing that we can measure is pressure. Okay? Pressure is the force a substance exerts, okay, on a surface. Okay? So for a gas, let's pretend this is like our same container here from earlier, the balloon. These black circles represent molecules of some gas, and we can see that they're traveling. Okay, boom. Some of them are traveling and they bounce off the surface of a wall. Some are traveling like this and bounce off the surface. We know that when those molecules hit the surface, as is outlined in red, they're causing a force to be exerted on that wall. They're pushing on the wall. Okay? And we can measure how much push is essentially happening on that wall. And the way we measure it is by measuring what's called the pressure. Okay? The units that we need to know for pressure of gases, okay, the first one is ATM, which stands for atmospheres. And at sea level, just to get a reference point, the air pressure around us is 1 atmosphere. So, at school, air pressure is about 1 ATM. Okay, the molecules at air pressure moving around are moving with a force of 1 ATM. There's also mmHg, which stands for millimeters of the element mercury, an older unit, but also common. Torr, T-O-R-R, and kPa, which stands for kilopascals. All of these units could show up in problems. We need to feel comfortable converting between them. So here are a few relationships to know. They're also going to be on your equation sheet. But 1 atmosphere is the same thing as 760 millimeters of mercury, which is the same thing as 760 torr, which is the same thing as 101.35 kilopascals. So with this information, you could convert between any single unit of pressure into another one. Just doing a simple train track, if you were given 2 ATM and asked to convert to something else, how to do that. We'll need to be able to do that for a bunch of different problems. The main conceptual thing to walk away with about pressure is this buzzword, collisions. Collisions are directly related to pressure. So if more of these molecules are hitting the walls, they're pushing on the walls more, that means there's a greater pressure. If there are fewer collisions, less collisions and less force on the wall, less pressure. And that's going to play a big role in our gas laws that we're going to review. There's 3 gas laws that we need to know. The first one is for pressure and temperature. Okay? Pressure and temperature are directly related. And the reason for this is if you increase the temperature of something, of a gas, you make those molecules move around faster. They have greater kinetic energy. Ke stands for kinetic energy, which means essentially their velocity, how fast they're moving. So if they're moving faster, that's going to increase the number of collisions, which is going to ultimately increase pressure. So we can see that if temperature goes up, pressure goes up. So since they're moving in the same direction, they are directly related. The equation that relates these is P1 over T1 equals P2 over T2, where 1 equals the initial conditions, what the pressure or temperature is to start, and 2 represents the final, after something is done to the gas. The only other thing that we need to recognize is how this could look graphically. So if we plotted temperature and pressure, we know that as temperature goes up, pressure is going to go up. So what that would look like on a curve is something like this. And we'll need to interpret those more analytically and quantitatively later. But for now, that's a good enough detail. Volume and temperature are also directly related, which means if you heat up a gas, the volume of that gas will go up. Okay? And the equation is the same. V1 over T1 equals V2 over T2, because they're directly related. Except now we have volume instead of pressure like we had up here. And lastly, for pressure and volume, these are indirectly related, which means they go in opposite directions. So if you increase the pressure of a gas, that's going to decrease its volume. Okay? Think about like a syringe. If you push on a syringe with more pressure, the volume shrinks. It gets smaller. So the way that would be quantitatively written is P1 times V1 equals P2 times V2. So you need to be able to use all 3 of these relationships quantitatively with numbers and plugging them in, and qualitatively using descriptions and explanations like are here. Last thing, graphically, since these are both directly related, if you heat a gas up, the volume gets bigger. And finally, indirectly, volume and pressure would be indirectly related with a negative downward slope. So we'll practice applying those in class, but I'm also going to give you a few now to work on. The last equation that we need to know is for something called the ideal gas law. Okay? What do we need to know about the ideal gas law? Well, the ideal gas law only applies to ideal gases. Well, what does that word ideal mean? It means perfect. So the ideal gas law is for gases that behave perfectly. So what does that mean? What are gases that behave perfectly? Okay. Gases that behave perfectly have no attraction or repulsion with each other. So this means if we're zooming in on a sample of a gas here, these molecules as they're flying around, they might get near each other. And we know normally that molecules might temporarily be attracted to each other because they're slightly positive or negative. Or they might be slightly repulsed because they're both positive or they're both negative. What we're assuming with an ideal gas is this doesn't happen. There's no attraction, there's no repulsion. These are just like balls on a pool table. Okay, there's no attraction, there's no repulsion. They just move around. They bounce off each other. If they bounce off each other, they do it. There's no attraction right here, like it says attraction between particles. That does not exist. If that doesn't exist, then that gas is considered an ideal gas, and we can do calculations with it much more simply. Okay. When is a gas ideal? Okay. Well, if we want to make a gas ideal, we want to make sure that it has no attractive or repulsive forces. So how can we minimize attraction and repulsion? Number one, we can increase the volume. So think about it. If we have a huge container, molecules are spread so far out from each other that it's very unlikely that they're going to bounce off each other because they're so spread out. And if it's less likely they're going to bounce, then it's less likely that we're going to have attraction and repulsion. Also, if we're at a high temperature, that means molecules are zooming around really fast, which means they have very little time to actually interact with each other. So if we increase volume and increase temperature, that's going to make a gas behave more ideally than it would otherwise. The ideal gases have a special formula, which is PV equals nRT, where P is pressure, V is volume, T is temperature. The only new things we need to know is what N represents. That's the number of moles of a gas. So here we're going to have to use our conversions between grams and moles, because I could give you a problem in grams and you have to convert it to moles before you plug it in. Also, R. This is something that's called the ideal gas constant. It's going to be on your AP equation sheet, but you might want to just start committing it to memory. It has a number. It's 0.08206, and the units are super important. Liters, atmospheres, I'm going to move my face around here. It's a little weird. Atmospheres per mole times Kelvin. Now, why is that important? The things to point out here, liters, atmospheres, and Kelvin. Since the units for R have liters, atmospheres, and Kelvin in it, that means anytime you do a problem, okay, the units for volume need to be liters. The units for temperature need to be in Kelvin, okay? And the units for pressure need to be in ATM. If they're not, you have to convert them first before you use them in this equation. Up here in the top right corner, I'm adding one small little detail. This is STP, which stands for standard temperature and pressure. This is a set of conditions that we record data about gases at so that we have a common set of data to look at and analyze and do experiments with. So what you need to know is what the pressure and the temperature is at STP. The pressure at STP is 1 atm, which is the same thing as 760 mmHg. And the temperature is 0 degrees Celsius, which is the same thing as 273 Kelvin. The only other thing that you need to know at STP, I know it feels like I'm adding a lot, is that 1 mole of a gas at STP has a volume of 22.4 liters. Once we have all this information, we can actually practice applying it, but I got to give it to you up front early. And it should also sound relatively familiar from previous classes. The only thing that might sound a little bit newer is this concept of a partial pressure. So this applies to mixtures of gases. So when we have, a beaker or something filled with more than one gas. Here's a sample. We have gas A, gas B, and gas C, and we combine them into one container to make a mixture. If we know the pressure of gas A, we're going to label that as P sub A, is what we would call it. Okay. The pressure of gas B would be P sub B, and the pressure of gas C would be P sub C. We could also call this the partial pressure of gas C. Now, why is that important? Because if we wanted to know the total pressure of this mixture, we need to know the partial pressures of each gas. Okay? Because the way to calculate the total pressure of a mixture, one of the ways, is by adding up all of the partial pressures, however many there are. So P sub A, P sub B, P sub C, on and on and on. If there's 4, 5, 6 gases, use more. If there's only 2, you just use those 2 and add them up. So for example here, let's say the partial pressure of gas A was 2 atm, this was 3 atm, and this was 5 atm. The total pressure, P sub T, would be equal to 5 plus 3 plus 2, all combined, 10 atm. Now, as we talked about earlier, pressure is a result of collisions. If there are more collisions, the pressure is going to increase. Well, what's one way you can have more collisions? Let's think about a simple analogy. Here's a balloon with 2 molecules in it. Here's one with a lot more. Which box is going to have more collisions out of A and B? B, clearly, because there's more molecules. So the number of molecules, or the number of moles, is going to affect the pressure. So the way that comes into play is with another equation, okay, that allows us to calculate the partial pressure of a gas. And this is also on your equation sheet. Here is that equation, okay? P sub T, P sub A is equal to P sub T times what's called chi A, okay? This represents the partial pressure of gas A. This represents the total pressure in the mixture. And this is something that's called the mole fraction of gas A. What that basically means is out of all of the gases in the mixture, what fraction of them are because of gas A? So the way that this is sometimes rewritten is moles of gas A over total moles. So this whole equation could be rewritten down below as the partial pressure of gas A is going to be equal to the total pressure of the gases times the moles of gas A over the total moles. And it's important to note that I could change this A to B or to C or whatever it is depending on what I'm trying to calculate. Since this is new, we're going to do one more problem together to test it out. So this says, consider the diagram below. Based on this information, which gas will have the greatest partial pressure, which will have the lowest, and what's the partial pressure of each gas if the total pressure is 4 atm? Okay, let's give this a shot. So I got a diagram here. What do I notice? I see I have gas A, B, and C. I see that one circle equals 1 mole. Okay, so I want to figure out which is going to have the greatest partial pressure. Well, we know that there's going to be more pressure happens when there's more collisions of molecules. More collisions happen when there's nothing given about speed, there's nothing about that, it's just which one has more molecules? Gas A. Because it has the most molecules. It's got 1, 2, 3, 4 compared to 3 and 1, which means it's going to have the most collisions, most pressure. What about problem B? You might be able to predict now in a pretty similar vein, which is going to have the lowest pressure? Gas C, because it has the fewest molecules. C is where we actually have to apply something now. This is asking us what is the partial pressure of each gas if the total pressure is 4. So we know that we could figure out the total pressure by adding up each of the partial pressures, but this equation isn't necessarily going to work because I don't know this, this, or this. I have 3 unknowns. So, not going to work. But what I do know is that for example, the partial pressure of gas A is equal to the total pressure times the mole ratio of gas A. So how can I use that information? Well, let's do some substitution. The partial pressure of A, we don't know, is equal to the total pressure, 4 atm, times the mole ratio of gas A. And remember, this represents how many moles of A we have out of the total moles. Think about it as, just kind of a percentage essentially. Well, how many moles of gas A do we have? 1, 2, 3, 4. And how many total moles do we have? Well, 4, 5, 6, 7, 8. So since half the moles are because of gas A, half the total pressure is going to be because of gas A. So this is essentially 4 times 1/2. So the partial pressure of gas A is going to be 2 atm. Pretty straightforward. Let's try the partial pressure of gas B now. Same idea. It's going to be the total pressure times the mole ratio of gas B. So the total pressure is still the same, 4 atm. Now the mole ratio of B is the same thing as here, but now it's just moles of B over total moles. So how many B moles do I have? 1, 2, 3. 3 over 8. So this is essentially, 3/8 of the total pressure is because of gas B. So if you do the math there, that comes out to 1.5 atm. There's 2 ways to solve for the last pressure. I want you to try to think about both of those ways, but what you should get for the partial pressure of C is 0.5 atmospheres. A lot of information in this video, but what you should walk away with is an understanding of how to apply the law of partial pressures in a problem like this, using moles and diagrams. What mole ratio or mole fraction actually means, right here, that's a vocab word. What partial pressure means, which is the gas because of the pressure because of just one gas in the system. The understanding of what makes a gas ideal up here. The ideal gas law and what N and R represent. What STP is. What our 3 gas laws are, their graph representations and their equations. As well as what the units of pressure are and how to convert between them. And finally, that about covers all of our vocab, and we're good to go with our introduction to gases. We will just practice with these concepts in class.